For this week's topic, we're going to cover the idea of variability. And to emphasize why this is important, I want to show you quiz scores from two classes. Let's say I give a class a 10-question quiz, and this is the number of answers each student got right. So looking at these two groups, which class would you rather be in? Would you rather be in Class A, or would you rather be in Class B? With Class A, one student completely fails the quiz, nothing right. A handful of students do not great, but not a 0. And then 2 students do fairly well on the quiz. Or would you rather be in Group B, where 3 students do awful on the quiz and 3 students do awesome on the quiz? Which one would you rather be in? Well, when comparing these two groups, what we learned last week was that we can take data and summarize it using a measure of central tendency. Now, looking at this data, we have the choice between the mean, the median, and the mode. Now, if we did the mode, looking at Group A, the mode is 4. The median is going to be the midpoint. When we have an even number of 6, it's going to be the middle, so between 4 and 5. And the mean. Let's take a look at the mean. Well, the mean is the sum of 0 plus 4, which is 4, plus 4, which is 8, plus 5, which is 13, plus 7, which is 20, plus 10, which is 30. So if I'm calculating x bar of A, I've got 30 divided by 1, 2, 3, 4, 5, 6, which is 5.0. Okay. So the mean, the median, the mode, somewhere between 4 and 5 for Group A. And if we look at Group B, the mode is either 0 or 10. The median is equal to, again, the median would be right here. It's a number between 1 and 9. Median is still 5. And the mean is 0 plus 0 is 0, plus 1 is 1, plus 9 is 10, plus 10 is 20, 20 plus 10 is 30, 30 divided by 6 is still 5. So here we have two groups, very similar measures of central tendency, but they're clearly not the same. In Group A, 5 of the 6 students at least get some credit. In Group B, really only 3 of the 6, I'm not sure I would count a 1 as much better than a 0, are getting the credit. So this is why we need to look at the variability of the distributions. And when I talk about variability, what I'm talking about is the amount of difference within the data set. So as we've talked about before, measures of central tendency indicate modality, which is the most frequent, and the symmetry of the distribution of scores. Because remember how we talked about positively and negatively skewed as the mean, the median, and the mode are relative to each other. And if all 3 of those are the same, then we have a distribution that is symmetrical. Whereas if we have distributions where the mode and the median are on one side or the other of the mean, we have a skewed distribution. So that's what central tendency gives us. Measures of variability give us how the scores themselves are different from each other. Is there a lot of variability in the scores, or is there a little bit of variability in the scores? So here's the way that graphically I like to think about this. We have 3 distributions. These are 3 different data sets of completely arbitrary and made up data. they have the same modality. So whatever number is down here, call it M, it has the exact same mean, median, and mode, which means that it's a symmetrical distribution. But clearly, these three distributions have variability differences. If we look at the first distribution, and we look at that curve, we notice how that curve is taller than the other two curves, and it's more compact, it's narrower. If we're body shaming, we would say that it's a skinnier or thinner one. If we look at distribution number 2, relative to number 1, same mean, median, and mode. So these two distributions are centered on the exact same point. However, 2 is shorter. It's got less area at that middle point, and there's more out here on the sides, in this area out here. There's more area spread out. And if we look at distribution number 3, this is the shortest one of all. It's also the widest one. Distribution number 3 has a lot of area out here. So these three distributions have different measures of variability. And what we need to do this week is to learn how to quantify, how to create a measure which tells us the width or the spread or the variability of our data sets, so that we can have a better understanding when we compare two groups like Class A and Class B. This is a picture of a weight stack. And the reason I took this picture is because I wanted to show how in everyday life, these curves that we use in the class, these normal bell-shaped curves, how we actually think they appear. And so let's imagine you're a major of exercise, sports, science, recreation, whatchamacallit. They keep changing their name here at Coastal, kinesiology. And one of your data points that you want to know is how much an individual lifts. So you have a couple of choices on how to collect that data. So you go over to the HTC Center and you pick one of the weight racks and you say, I'm going to sit and I'm just going to record where everybody puts the pin in the weight rack, because that's how these things work. The weight rack, each plate has a hole, and you stick the pin in the hole. The pin is usually an L-shaped, or it has a hook to it so that you can grab it with your fingers. But the pole goes in through, and then it connects that weight and every weight above it to the bar that gets lifted. You'll notice that looking at the picture, you can see that there's some wear. So right up here, the paint that has painted the weight has been rubbed off by the insertion of the pin. Usually, like I said, it's an L shape. So what you see is the how much gets worn away when you put that plate in, usually from above. Now looking at this, you just see a bunch of paint that needs to be fixed. But what I see when I look at this is I see a distribution. What I see is a line through here, and what I see is a curve. It's a subtle curve. It's very light. But the amount of usage in the 45 to probably 70 or 80 pins is a lot more than the usage that if you look down here, where there's hardly any point. So the frequency by which people are using the 150-pound plate is pretty small. Just like if you look up here at the top at 15 and 20 pounds, there's not a lot taken out on these ones as well. Why? Well, let's think about this. If you're going to sit down and you're going to do a rep, you're going to do 3 sets of 15 reps. You're working on your back today. Are you going to put the pin in at 15 pounds? Some of us have pets that weigh more than 15 pounds. Is that a workout for you? 15 pounds between your 2 arms pulling down, working on those back shoulders? No, that's hardly any weight. Grocery bags weigh more than 15 pounds. Conversely, if you're looking to buy some weights, do you need to pay extra as the weight bench goes up to, let's say, 200 pounds? Probably not. There aren't a lot of people that are doing pull downs of 200 pounds. It looks like, according to this, there aren't a lot of people at our gym that are doing much more than 120 pounds. It looks like the bulk of the work is being done here in the center, the 45 to 90 pound range. So I spent a little bit of time on this because I want you to sort of understand that, yes, these curves that we draw, this standard normal curve, it's just a math equation. I'll show you at the end of the class what the equation looks like. But in real life, this normal distribution, we can see it. We can see it in shoe size. We can see it in the amount of weight that people do at the gym. We can see it in the amount of time that people take in a parking lot to pull their cars out from a parking spot. We see this natural bell-shaped curve occurring in lots of things, even test scores. So let's look at some measures of variability. The simplest measure of variability is one called the range. The range gives us the gap between the 2 ends of the distribution. So you take the highest score and you subtract the lowest score. When you report the range, you report it as this variable ranges between lower score and upper score. So let's go back to our 2 groups. And so what would the range be of group A? Well, the range is 10 to 0. For group B, the range is from 10 to 0. So as a measure of variability, not exactly the best, because it only really is including 2 data points. But the range, that's what it is. Easy to compute. Very easy. When you take the maximum and you subtract the minimum, those are your 2 things. That's the easiest thing to do. But even though it's just a very simple range, it does give us some information about our sample. So going back, it doesn't really work for the test because somebody got the highest score and somebody got the lowest score. But let's look back at this one. What is the range of values for our weight set? Well, I know you can't see this as well as I can because I've got the picture right here in front of me. But if I were making weights, I wouldn't include anything that weighs less than 20 pounds, and I also wouldn't include anything that is more than 120 pounds. If you're going to be lifting more than 120 pounds, you're not going to be doing it on a pull-down machine. All right, so you can just get rid of these ones down here. That's a capacity. It's sort of like, let's ask ourselves honestly, in buying an automobile, there are cars out there that can go over 200 miles per hour. But when was the last time you had the opportunity to drive that fast? Do you need a Bugatti Veyron to drive up and down 501? No, because you can't, between the traffic and the stoplights, probably even get the car up to 200 miles per hour. That's a range of top speed that you don't need. Can you get a Chevy Traverse over 100 miles per hour? Perhaps I have experience doing that. It might have happened one time. But I don't need to buy an SUV that can go 200 miles per hour. So the range itself, looking at, say, our driving habits, and asking ourselves, do we need a car like a Dodge Hellcat that has 750 horsepower? Probably not. I don't get a lot of opportunities driving between Carolina Forest Boulevard and campus to use all 750 horsepower. The problem with the range? Well, it's only based on 2 scores. And it doesn't really, because it's only based on 2 scores, does it really accurately reflect the amount of variability in the entire distribution? Because let's go back to our example of A and B. The range was exactly the same, 10 to 0. Does that represent how much variability there is? Not so much. So with the range, the weakness includes that it only has the 2 scores, the maximum and the minimum. And if you have an extreme score, an outlier, that's going to affect your range. I think looking at Group A, given how poorly the class did, I think this 10 here we could say is an outlier. And there's always that one person that ruins the curve, right? The professor comes in and says, well, everybody, the average on the exam was 65, but one of you got a 98, so I can only curve the exam 2 points. And you're cursing that person or sitting there trying not to crack a smile because you're the one that got the 98, and everybody in the class now hates you, so you don't want to let them know that you got the 98. Plus they'll give you a lot of grief, and you'll have to help a lot of people if they find out you're the smart one in the class. Okay, so an outlier, somebody that's on the edge that outperforms the rest of the class, that's going to screw up the range. To solve this problem of the outliers affecting the range, what we can use instead is known as the interquartile range. The way that the interquartile range works is what you're trying to do is identify the middle 50% of the scores. So we start at 0%, we have 100%. If this is 50, 75, and 25, what we're looking for is the range of from here to here. So what is the middle 50% of the scores? So that way, if we have outliers on our edges that are pushing the range outwards, we can avoid the effect of those outliers in our range. So how do we get that? Very similar to computing the median score. So we're asking ourselves, what's the 25th score and the 75th percentile score? Well, it requires to know what n is. How many do we have? And the n minus n divided by 4th scores. So let's say we have, back to our example, we have 6 students. Grabbing my calculator to look so I don't look like an idiot. 6 minus 6 divided by 4. 6 divided by 4 is 1.5. So 6 minus 1.5 Yeah, I'm actually typing that out. I know what you guys are doing. 6 minus 1.5 is 4.5. 6 divided by 4 plus 1, that's 1.5 plus 1, that's 2.5. So what are we going to do here? We're going to take the fifth score minus the third score? Okay. Fifth score minus the third score. So the interquartile range is 7 minus 4. The width of the interquartile range is 3. Let's take the fifth score minus the third score here. 10 minus 1 equals 9. So the interquartile range for group A is 3, while the interquartile range for group B is 9. Okay, so here we have a better measure of variability. It seems that in group B there is more variability than there is in group A. Again, the strengths of this, it's great because it reduces the influence of outliers. The problem is you ignore half of your scores. Data is precious. You go through a lot in collecting your data, and here you're saying, no, I just need the middle 50%. I had to collect twice as much data to figure out who the middle 50% were, but I'm not going to look at the 25 on the outsides. So here's what we're going to use as a solution. There's one called the variance. The variance, denoted as S squared. Okay. The variance as a measure is based on all of the scores in the distribution. So that means we're going to use each and every score when we calculate this. The more variables we have, or excuse me, the more observations we have in our data set, the more calculations it's going to take to compute the variance. Not that big of a deal. What we're doing when we calculate the variance, we're measuring this variability as the extent to which the scores differ or deviate from the mean. Okay, just a little sidebar here. So if you're a sports watcher like I am, and you're watching like baseball, for instance, hitters will go on a hot streak where in a span of 10 games, they might do something crazy like hit for 600 batting average and 8 home runs in 10 games. And some announcer will go, well, this is great, but at some point, he's going to regress to the mean. First of all, regress to me means something different than it does to them. All right? What he is trying to say, the sports announcer, is this is great, but at some point they're going to cool off and go back to being a 232 hitter. You can't expect them to stay at 600 forever. Regress to the mean is this idea that right now his performance is far away from what it would typically be. It's an outlier. By regressing to the mean, what we're saying is this is highly different from the typical performance this person would have. A lot of variance. So how do you get to the variance? Well, this is what it is. And this actually looks like a formula. Somebody here went, math. Not a problem. We have this. This is not that difficult. Let's do our notation first. Let's do, remember, if we're feeling a little anxious, we always have PEMDAS. PEMDAS is our order of operations. What order are we going to tackle this in? The first thing we do, we're going to do what's inside the parentheses, which stands for the P. So what we're going to have to do is we're going to have to calculate the difference. You see that subtraction sign right there? The difference between our observation and the mean for our group. Okay? So, here's what we can do. Let's go back to our first group here. Let's take a look at these scores. 0, 4, 4, 5, 7, 10. Zero, 4, 4, 5, 7, 10. Now we already calculated the mean. That's our x. We already calculated the mean for this group. It was 5.0. Okay. I can just write this whole column of 5s. That's the data we have. Next step, subtract these two numbers. So I'm going to create a third column here. That's x minus x bar. What is 0 minus 5? That's a negative 5. 4 minus 5 is a negative 1. 5 minus 5 is 0. 7 minus 5 is 2. And 10 minus 5 is 5. The difference from the mean. Now, if you're paying attention to last week, you'll notice that I spent a second and talked about how all of the sum of the differences from the mean, if you've done this correctly, should add up to 0. So what do I have here? I have a negative 5, a negative 1, and a negative 1. 5, 1, and 1 is 7. On the positive side, I have a 2 and a 5. That's a 7. If I were to add all of these up together, I would get 0. So let's take a look at this equation. The sum of the difference squared. So what do we do next? Well, if we do this wrong, and we say, oh, well, the sum of the difference is 0, because you just added those all up, and they add up to 0, and then we square 0, we have a problem, because 0 squared, 0 times 0 is 0. Nothing. That's not going to work. That's because you're doing it wrong. Okay? PEMDAS, parentheses, which we did first, exponents. So we need to square this. X minus x bar in the parentheses squared. What's 5 squared? It's 25. 1 squared is 1. Negative 1 squared is 1. 0 squared, still 0. 2 times 2, 4. 5 times 5, 25. Okay. So we've done this operation. We've done this operation. The last remaining operation in our numerator is to sum it up. So we just need to take the sum of this. 25 plus 1 plus 1 plus 4 plus 25. Well, the two 25s is 50, 54, 55, 56. N minus 1. How many people did we have in our groups? We had 6 people in our groups. 6 minus 1 is 5. 56 divided by 5. And yeah, I'm getting my calculator out. 56 divided by 5, 11.2. Okay. All right. Let's do B. B was 2 zeros, 1, 9, and 10. And through the magic of my computer, see if I can just erase enough. Okay. Let's see. And I already forgot what those numbers were. They were 2 zeros, 1, 9, 2 tens. 2 zeros, a 1, a 9, and 2 tens. Okay, so let's go back through my steps. First step is to do what's in the parentheses. It's the P of PEMDAS. 0 minus 5, minus 5. 1 minus 5 is minus 4. 9 minus 5 is a positive 4. 10 minus 5 is a positive 5. Squaring these, I got 25, 25, 16, 16, 25, 25. That's them squared. Next, add it all together. 1, 2, 3, 4 25s is 100, and 2 16s is 32. I've got 132 divided by 5. Yeah, I'm still going to go back and 132 divided by 5. 26.4. Now, hopefully you can see with the variance that there is a large difference between our 11.2 and our 26.4. What is this measuring? This is measuring how much the squared distance from the mean is on average. That's the variance. Remember, it's the squared distance from the mean on average. Now somebody in their head is going, wait a minute, it's not on average because you divided it by 5 instead of 6. Well, we lost something called a degree of freedom. And a degree of freedom is part of what you are theoretically using up when you calculate a statistic. So we had 6 observations, and when we used the mean, we used up one of our degrees of freedom to generate our variance. It's going to come back later in the class. I don't need you to be experts in it now. I just need you to see that sometimes we're using n minus 1 because we've used a statistic in the calculation of another statistic. Okay? In your textbooks, table 4.2, they pretty much go through the same thing with a different example. I'm going to skip over it because I just did a better example. Now, this the variance is nice. However, that square in there sometimes throws people off because it's the squared distance. And you calculate a statistic of 26 when the range of your values only goes between 0 and 10. And so that can screw some people up. But also because of the squares, you'll notice that, man, that 26 was a lot different than the 11.2 that we got. So does that mean it has that many times the variance? No. What we actually most frequently use is called the standard deviation. And if you're having a flashback to middle school, yes, same standard deviation. All right, S. What we're trying to do in the standard deviation is to take out that square. We had to do it because the sum of the difference of the means always adds up to 0. So squaring something is a very popular option, but it takes away some of the meaning from it. So what we're going to do is we're actually going to take the square root of the variance. So we have our variance. If we take the square root of our variance, that leaves us with the standard deviation. Now, if you got your phone out, what you need to do is to take your calculator, if you're using your phone calculator, and turn it sideways. When you do that, you get more buttons. And what you're looking for is the check mark. So I'm going to go back to our data here. And I'm going to type in 11.2 and then hit the check mark button. And it doesn't like that. It actually wants you to do the check mark first and then do 11.2, then close the parentheses. And my standard deviation is 3.346. I'm going to round that to 3.35. Then I'm going to clear, and I'm going to do the standard deviation of 26.4, or sorry, the square root. And that is 5.138, which is 5.14. Okay, so there's still a gap between the two. This one still has a higher standard deviation. So in the formulas, you'll notice that the main difference between the standard deviation and the variance is whether or not you're computing the variance under a square root or not. Same thing, just one extra step. The standard deviation, when we use it in a sample, is a lowercase s. When we're using it as a representation of the population, that parameter is a sigma. Okay, so a little bit of Greek letters. That's a uppercase sigma, and that's a lowercase sigma. This sigma, the uppercase, is our summation sign, which is adding all together. This lowercase sigma is our standard deviation. Didn't know you'd have to do a foreign language here, did you? But, yep. It's all Greek to me. Okay. So what do we have here? Well, we went through a few different options. The range and the interquartile range are okay, but again, how much variation are you using in your data set when you're only using half of the observations or 2 of your observations? That's nice, but there's always something better, something that uses everything, and that is the variance and its squared cousin, the standard deviation. These are the two that you should be thinking about. What are we using with standard deviation and variance? Well, we're calculating variability. How much difference is there within our distribution from each other? All right. What are we going to do next? Well, next we're going to use the magical properties of the standard distribution to figure out how far away we are when we have an attempt to compare ourselves to the mean as part of this distribution. Now, one of the neat things about math, where sometimes it's magical, we have this thing with normal distributions. It's called the empirical rule. And the empirical rule helps us understand the area under the curve and how much area is under the curve at a distance away from the mean. So let me just sort of explain this. So again, all of our data is in a curve. It represents from the minimum to the maximum. And remember, our midpoint is usually at our mean, which in a symmetrical curve is also our mean, median, and mode. Now, the shape of the curve, right, whether it's tall and skinny or short and wide, depends upon the amount of variation or variability in our sample. So, using the standard deviation, That's important to understand the shape of our curve. The curve shape is the same. It's a curve. But the width and the height of that are affected by the standard deviation, or the variance. It turns out that when you go out one standard deviation in either direction, so if we go plus a standard deviation, so a mean plus a standard deviation, or a mean minus a standard deviation, that 68% of our observations should fall within one standard deviation, plus one and minus one. 68% should. If you go out two standard deviations, in either direction, then 95% will fall between the mean and the two standard deviations. If you want to go out to 3, it's 99.7%. Why is this useful? Well, what we're going to do in the next part of the class is we're going to try to quantify the distance between ourselves as individuals, or a single observation, and the mean. And we're going to try to see how likely it is, or where we are, or what percentile we're at. So the next class, what we're going to do is we're going to sort of take a twist on this and start using this area under the curve and focus on that. Okay. This empirical rule comes from the equation for a standard normal distribution. And so I don't expect you to learn this or do this. I just want to sort of show it to you and take 1 minute. Again, try to alleviate any anxiety of the math that you have. This top section here is the equation. Wow, that was a really badly drawn line. This part up here is the equation that you can use to graph a standard normal curve. And when we look at it, we see a lot of letters in Greek letters. Y is the point, the outcome. 1 is the number 1. 2 is what you'd expect, the number 2. Pi, that's actually that number, the constant pi. E is a logarithmic function. This is about where I sort of stopped in my math, understanding log functions. And it's a number. It's also a constant. X is our observation. And mu, this is our population mean. Squared is just squaring something divided by 2, and then here we go. Here's our friend, our population standard deviation. So these things help give the curve its shape. Again, I don't expect you to memorize this. I just want you to understand how important the mean and the standard deviation are to understanding what our curves are. Okay. So what we're going to do next class is, now that we have this idea, we have an idea of central tendency, we have an idea of variability, what we're going to do is we're going to delve a little bit more into what this normal distribution is and understand how it works. So that's going to be next section. Again, you've watched this. Feel free to go ahead and practice the section exercises. There's a video where I go through the section exercises in the textbook, and then once you've watched the video of me practicing and you're comfortable with these ideas, you can go ahead and take the section exercise that's on Moodle, the little quiz. And if after watching my video of going through some exercises, if you still need additional help, there's help in the help section. Or get a hold of me and I'll walk you through it. Thank you.